Section 3.7. We're still in chapter 3, so we're still dealing with applications of derivative. In this case, we're going to look at optimization problems. So optimization problems are dealing with finding a minimum or a maximum, because usually if we're trying to solve a problem, we generally want to get our best solution, which is what we mean by optimization. Usually this is going to involve finding either a maximum, what's the maximum profit, what's the minimum cost, something like that. That's going to involve finding extrema, which you can do with derivatives. Hey, isn't that cool? Okay, so we're going to work through this example here. We want to make a box. We want a square base, a surface area of 108 square inches, and we want to have the maximum volume. So this surface area of 100 square inches, that would be kind of a constraint, what's limiting us. And we want a square base. So we want maximum volume. So volume is what we want to find the extrema of. So we find the volume of this box is going to be length times width times height, or x squared h. This we're going to call, as soon as my thing disappears, the primary equation. Oh, it really wants to be there. This is the equation we're going to have to take the derivative of. However, it has two variables, x and h. And we're not doing a related rates problem here because we're not changing one to see how the other changes. So we need to get this down to one variable. So that's where we use our constraint here. We have 108 square inches. So that's the surface area. So we take the base plus the 4 sides. We get this formula for surface area. With here we have x and h. We can write a relation between the two. We need to solve this for one variable to substitute in the other, and it would be silly to go for x because it's quadratic. Yuck. So we solve this. This, by the way, we call the secondary equation. We're going to solve this for h. And now we can plug h into the original equation to get our new formula for volume, which is now 27x minus x cubed over 4. This is all in terms of x, so we can find the derivative and find the value of x that maximizes it. This is also not a problem that's not too bad to find the derivative. We also, though, want to look at what's a feasible domain, because we can't just have any value for x. So in this case, x has to be positive because I can't have a negative side, and it has to be less than the square root of 108, because if x is the square root of 108, then 108 square inches gives me the base and there's no height. So I have to be between those two numbers. Now, strictly speaking, I can't have a box with a length 0. I can't have a box with a length square root of 108. So why did we have equal to? Because to guarantee a maximum value, we need to have a closed interval. If it's not a closed interval, we cannot guarantee a maximum value. But also, by Rolle's theorem, we know that there is going to be a critical value. I don't necessarily know it's going to be, well, it has to be a maximum because the endpoints are going to be at 0. And so it can't be negative, so it has to be positive, so it has to be a maximum. But that's, again, Rolle's theorem says, hey, we're in good shape. So we take the derivative, set the derivative equal to 0, and we get x equals plus or minus 6. But, again, our interval was between 0 and the square root of 108, so I can't use negative 6, so I just use 6. So, again, to find the absolute maximum, I check the endpoints at 0, at 6, or 0 and the square root of 108, and I also check it at 6, I get at 6, my volume is 108. That's just kind of funky, isn't it? So the maximum volume is 108 cubic inches when the length of x is, when the length of the side of the box is 6. So that was an optimization problem, and that's pretty much what we're doing. I kind of have, what I have left is I have guidelines here for solving these problems, and then we're going to do a few more, give you a chance to try it, and then I'll work them through with you. So first thing you want to do, identify all the given quantities and the quantities to be determined. This is very similar to doing the related rates problems. If possible, make a sketch. Sometimes that helps you relate the two. Find your primary equation. That gives you what are you trying to maximize. You want an equation for that variable. Now we need to make sure it's down, the primary equation is just one single independent variable, which may mean you have to find some secondary equations that relate the other variables to substitute in and work that down to get it down to one equation with just one independent variable. You want to look at the feasible domain. What numbers make sense? This is also, again, to find the maximum, you need an interval. To guarantee you're going to have a maximum or a minimum, you need an interval, and it might be one of the endpoints. So you have to have a closed interval. So you need to find those feasible values, and then you determine the maximum and the minimum using the stuff we did beginning of the chapter. So give this one a try. Pause video, try to do this one on your own, then bring it back up and see what I got. Not that. So, if you want, which points of the graph of f of x are closest to the point 12, 0? So I'm going to start off with the distance formula. Distance equals well, I'm going to do it this way. Distance squared equals x2 minus x1 squared plus y2 minus y1 squared. That's your general distance formula. It's Pythagorean theorem, right? So I'm going to say if I make this x2, y2, and I make this x1, y1, I can start off with 12 minus x squared plus 0 minus the square root of x minus 8 squared. So this is going to be 144 minus 24x plus x squared plus x minus 8. So d squared is going to be x squared minus 23x plus 136. Or d is, now I'll take the square root of that. X squared minus 23x plus 136. Now if I want to look my feasible domain, if I look on here, x has to be greater than or equal to 8. if I kind of look at what that graph is going to look like, we're going to start here is 8. It's going to be a square root going up like that. And if we go, here's our point 12, 0. We know that any point from here on is going to can be the closest value, because these points are all going to be farthest away from the point at 12. So I'm going to put this on a domain of 8 to 12. So we're already in terms of just one variable, so we're going to find the derivative. So I have a square root function, so this is going to be 1/2 times x squared minus 23x plus 136 to negative 1/2. That's an awful color. Let's use a different color here. Sorry about that. Not do that, not do that. Try this again. The derivative is going to be 1/2 x squared minus 23x plus 136 to the negative 1/2 times the derivative of the inside, which is going to be 2x minus 23, or 2x minus 23 over 2 times the square root of x squared minus 23x plus 136. Now we know this cannot be 0 because this is just d. And the distance between 12, 0 and this graph will never be 0 and will never be negative. So I don't have to worry about that. If I want to set this equal to 0, I can just go 2x minus 23 equals 0. X is going to be 11.5. If I go plug this into my formula, my distance at the endpoints, so my distance at 8 is going to just be 4. My distance at 12 is going to be 2. And my distance at 11.5 is going to be 1.936. Again, I did this by plugging into my formula right here for D. So I say this is my minimum. So my answer is the point 11.5, 1.936 is the point on the graph f of x minus 8 is closest to the point 12, 0. Ready for another one? So here we got a picture for you to make things a little easier. We got 2 posts. Whoops, I don't want to do that. 2 posts, one's 12 foot high, one's 28 feet high. They're 30 feet across. We're going to put a guy wire attached to a post here. So we'll go down from there and then up to here. We want the least amount of wire. So we've broken this out to throw this, said if this is, we're determining x to be how many feet we are from y, or sorry, from the post or the stake, then if the whole thing's 30, this other distance is 30 minus x. So give this one a try. See what you can do with this. We want the least amount of wire. I think I want a lot more room on here. Oh, I'll leave that up there. So again, I'm going to draw the picture that we had there. Do 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 do. Okay. Okay. So, and we said this was 12. This is a right angle. This is 28. This is a right angle. This is x. This is 30 minus x. This we said y. And this we said was z. And so my equation, w, is how much wire we need, is going to be y plus z. This is primary. But now we don't want, in this case, we need to get this down to one variable. And I can't really get y in terms of z or z in terms of y. So that's why I'm going to use a third variable here. And we're going to come along and use good old Pythagoras and say for y squared equals 12 squared plus x squared. So y equals the square root of 144 plus x squared. Z equals, z squared is 28 squared plus 30 minus x squared. So z is going to equal the square root of 28 squared is 784 plus 900 minus 60x plus x squared. So z is going to be the square root of x squared minus 60x plus 1684. These are my secondary equations. We plug both of them into here, and we're going to get w equals the square root of 144 plus x squared plus the square root of x squared minus 60x plus 1684. And my feasible domain, since x is going to be, this nail is going to be between these two posts, x has to be between 0 and 30. So we're looking at this on the interval of 0 to 30. And again, the closed interval we have here. Because we want to check what happens if we just put the stake here. What happens if we just put the stake here? So let's find the derivative of this puppy. Don't forget we got a chain rule. So we got 1/2 times 144 plus x squared to the negative 1/2 times the derivative, which would be 2x, plus 1/2 times x squared minus 60x plus 1864 times the derivative, to the negative 1/2 times the derivative of the inside, which is 2x minus 60. So let's see what we can do with that. 1/2 times 2x is just going to be give me x over the square root of 144 plus x squared. Here I'm going to take 1/2 into here, make that a 1x and make this 30. So I'm going to get x minus 30 over the square root of x squared minus 60x plus 1684. And all I got to do is solve this for 0. Okay, so on this one, again, sometimes we grab these examples to show you some other things we can do with this. Whoops, I didn't want that. If I'm solving this for 0, I'm going to take one of these to the other side. So I'm going to say x over the square root of 144 plus x squared equals the opposite of x minus 30 over the square root of x squared minus 60x plus 1684. But instead of putting the opposite of a difference here, what I'm just going to do, I need to make this a little smaller. I'm just going to switch my subtraction order. Because if I make this 30 minus x, that's going to be the opposite of x minus 30. Then I'm going to multiply through by my common denominator, which is going to be the square root of 144 minus x squared times the square root of blah. Here we're going to, well, I'll write it out. Square root of x squared minus 60x plus 1684. And this I take. Square root of 144 plus x squared times the square root of x squared minus 60x plus 1684. And those cancel and those cancel. And I will get x times the square root, x squared minus 60x plus 1684 equals 30 minus x times the square root of 144 minus x squared. This is now, at this point, this is the algebra stuff that just messes you up. That's the thing that makes this problem the worst. I got square roots in there, so I'm going to square both sides. If I square a product, I can square each factor. So this is just x squared times 60x 1684. This is just 30 minus x squared times 144 minus x squared. Now, I'm going to let you do all of that work, go through there. You should be able to get down to 0 equals 640x squared plus 8640x minus 129,600. And we just have to factor that, right? Well, I'm going to start off. When I started factoring this, I thought, wouldn't it be nice if 640 was a common factor? So if we went 640, this would get down to x squared, but 640 doesn't go into this one evenly. This gives me 13.5x. And it doesn't go into this one evenly. It goes into 200 and 2.5. But they're both 0.5, so we're saying, okay, instead of taking out 640, I can take out 320. That's going to give you 2x squared plus 27x minus 405. Now, you wouldn't have to factor. You could, because even at that point, does this factor? What are the factors of 405? I'm done playing with that. I'm just going to go straight to quadratic formula. You could have gone to the quadratic formula at this point here. Say x equals the opposite of 27 plus or minus the square root 27 squared minus 4 times 2 times negative 405 all over 2 times 2. Because I don't care about the 320, I'm trying to equal 0. And I'm going to get x equals 9, or x equals a negative 22.5. This is not in my feasible domain, so x should equal 9. Now, what's the question actually asking me? Actually asking me where should the stake be placed to use the least amount of wire. I don't need to know how much wire I need. I just need to know where should the stake be placed. So it should be staked 9 feet from the 12-foot pole. Again, you can't just say x equals 9 here. Explain what your answer means. We got one more question to do. It's kind of a doozy, so I'm going to leave that one for a separate video. This one's already 26 minutes long, so I'm going to, at this point, just give you your homework, and then if you want to, I would say go try that other problem with the circle, see what you can do with it, and I'll come back and make a separate video, and we'll work through doing that problem.